Good afternoon all. Myself Arjun V, Assistant Professor, Department of Civil Engineering, VVC Mysore. I will be the MC for today's GATE training program. I welcome all of you to the session 1 of day 5 on concrete structures by Professor Arjun V. In this session, we are going to discuss about the concrete structures. So, if it, Professor Arjun V is an assistant professor having over 6 years of teaching and research experience, and he obtained his bachelor degree in civil engineering from PS College of Engineering, Mandya, and master's degree in structural engineering from the National Institute of Engineering, Mysore. He offers consultancy in design and NDT evaluation of RC structures. So today we're going to speak about concrete structures, session 2 actually. So with the short note, I request Professor Arjun to take over the session. Over to Professor Arjun.
Thank you, Professor Rajit, for the introduction. Firstly, I would like to thank VBC management members and the organizing team for making me a part of GATE training 2021. My topic is concrete structures. This is the second session. This is the second session on the concrete structure. So those who have missed the first session, you can watch the video which is in the playlist, and few of the highlights of previous session, the very important highlights or key points of the previous sessions are the formulas to be remembered in case of singly reinforced section. In case of singly reinforced section, what are the formulas to be remembered? Or the first one is depth of neutral axis. So the depth of neutral axis is computed using the equation XU is equal to 0.87 Fy AST divided by 0.36 FCK into B. So this is the formula we can use in order to determine the depth of neutral axis. So the limiting depth of neutral axis, you have to remember these values. In case of FE 550 grade or FE 600 grade is given, what you can do is you can use the strain diagram. In case of limit state design, we will make use of linear strain diagram, whereas in case of working stress method, we will be using linear stress relationship. Okay. And the total compressive force as per IS 456 area of stress block from the stress block is Cu is equal to 0.36 FCKB into XU will give the total compressive force resisted by the concrete section. And the total tensile force resisted by the steel section is given by Tu is equal to 0.87 Fy AST is the total tensile force that can be resisted by steel reinforcement. Okay, and coming to the moment of resistance, the moment of resistance in case of under reinforced section, may be computed. In case of under reinforced section, the governing factor will be the tensile force. So it is going to failure by tension. So Tu into lever arm distance will give you the total moment of resistance. In case of balanced and over reinforced section, the predominant factor is compression. It is going to fail suddenly. So you can determine the limiting moment of resistance as Cu into lever arm distance. So the lever arm distance for singly reinforced section will be, it is D minus 0.42 times of XU. Okay. And also the PT limit, the percentage of tensile reinforcement will be equal to 41.4 into FCK divided by Fy into XU max by D. So this formula is very important in order to solve the problems. Okay. So apart from that, the general things what you have to remember in case of beams are AST minimum. The minimum AST in case of flexural members, flexural beam, the beam subjected to flexure is AST minimum is given by 0.85 times of BD divided by Fy. So these things are specified as per IS 456 2000. Okay, so and also the spacing of shear reinforcement shall be lesser of following. First one is 0.75 times of D, where D is the effective depth of the beam, 300 mm, or SV, which is equal to 0.87 Fy ASV D divided by VUS. So these three formulas will be useful in solving the problems, in solving the 2 mark problem. Sometimes they will ask you the problems in order to find the exact spacing of the shear reinforcement. So this has been given in asked in one of the gate examination. Okay, and also we have also discussed about the bond strength or development strength has been discussed in the previous class. And the important thing what you have to remember in case of bond stress is the variation of bond stress is parabola. And if you consider this, the variation will be parabola. So the bond strength will be maximum. This is parabola. The bond strength will be maximum at the face of the support. Okay, so if you pull these things you have to remember. Okay, coming to the next concept, that is design of slabs. Okay, so in designing a reinforced concrete slab, we have to remember few of the parameters or few of the things we have to keep in mind, among which the first one is effective span. What is this effective span? So as per IS 456 2000, for a simply supported slab or a beam, the effective span is considered as lesser of the following. The first one is center to center of the support, or it should be considered as clear span plus effective depth. That means if you consider the slab, if you consider a slab here, if it is simply supported over a support, okay, so let this be the main reinforcement. So your effective depth will be up to the center of the reinforcement. So this will be your effective depth. So the distance between the support will be called as clear span, which is represented usually by small letter slab. In case of simply supported slab, the effective length should be always equal to L plus half of the bearing width on either side. Okay, so we have two supports here. Let us consider this as BW, bearing width. Okay, so BW on one side plus BW on other side will give you the effective length, or the center to center distance will be considered as effective length, or effective length can also be considered as L plus D. Among these two value, whichever is lesser, that should be considered as your effective length for the calculation of moment. For the calculation of moment and shear force, you have to consider the effective length as L, center to center distance between the supports, or the clear span plus effective depth in case of a simply supported slab. Okay, so in case of continuous slab, there will be a two category. If okay, if you consider a continuous slab, there will be a two category. the first case is when the width of the support is less than L by 12. Okay, where L is the clear span between the supports. Okay, so L by 12 or 600 mm, whichever is lesser. Okay, so you have to consider the case one as in case of continuous slab. First, you have to check whether the support width is less than L by 12 or not, and also if it is less than 600 mm. Out of these two, whichever is minimum, that should be considered as the case one. If you consider, let us call this as 8 meter. Okay, if you consider this as length as 8 meter, so L by 12 is clear span is 8, so clear span 8 by 8000 divided by 12 is 666. Okay, 3 by out of these two, 600 mm is lesser. Okay, so if the width of the support is less than 600 mm, if the width of the support is less than 600 mm, then the effective length will be considered. Similar to simply supported slab. That is, either we have to consider between the center to center of the support. So center to center of the support should be considered as effective length, or it should be L plus D, L plus effective length. So that should be the first case. In the case two is when the width of the support is greater than L by 12 or 600 mm. So in such a cases, there will be again three categories. Let me draw the diagram. Suppose if one end is fixed, if one end is fixed, okay, if for the first, in the case two, for the end span with one end fixed and other end is continuous, or for intermediate spans, the effective span shall be clear span between the supports. That means if one of the support is fixed and the remaining supports are continuous, in such a cases, you have to consider the effective length as a clear span. LE will be equal to L. Okay, let us call this as L1. Even for the intermediate spans, LE should be always equal to L. That is clear span. Next, for the end span with one end free and the other end is continuous, let us consider this the span 3. Okay, let us consider the span 3, L3. Okay, in such a cases, here the one end is free and the other end towards left is continuous. So in such a cases, the effective span shall be equal to the clear span plus half of the effective depth. So L3 is equal to clear span plus D by 2. Okay, or slab or the clear span plus half of the width of the discontinuous support. Okay, so whichever is lesser, that should be considered as effective span. In case of the spans with roller or rocket bearings, the effective span shall be always considered as center to center distance between the supports. Okay, so in case of roller supports, say example, there is a continuous support which is resting on roller support. If there is a continuous slab which is resting on roller, then in such a cases, it should be always the effective length should be always considered as center to center distance between the supports. Okay, so next one is design of cantilever slab. Okay, in case of cantilever slab, the effective length of the cantilever slab shall be taken as its length to the face of the support and half of the depth except where it forms the end of a continuous beam, where the length to be considered as center of the support. Okay, say example, if there is a cantilever slab, okay, if this is the support, then the effective length of such slab will be always equal to clear span plus half of the effective depth. So this should be the effective length of the cantilever slab. In case of frames, it is always the center to center distance shall be considered as the effective length of the slab. Okay, so while designing a slab, the most common classification what we do in a slab is one-way slab and two-way slab. So this one-way slab and two-way slab classification is based on the predominant bending. If the slab bends in both shorter direction as well as longer direction, then it will be considered as two-way slab. If the bending in a slab is predominant only on the one direction, then such a type of slabs are called as one-way slab. Okay, so if the bending is going to happen in both the direction, predominant bending is occurring on both the dimensions, then it will be considered as two-way slab. If the bending is only in the one direction, then it will be called as one-way slab. Okay, so in order to determine whether it is a one-way slab or a two-way slab, we usually use the span ratio, that is Ly by Lx, where Ly is the span in longer direction, and Lx is the span in shorter direction. Okay, so if Ly by Lx is greater than 2, we will usually design it as one-way slab. If Ly by Lx is less than or equal to 2, then it will be designed as a two-way slab. Okay, so you draw a diagram. So the shorter span should be always considered as Lx. So this is the plan, and the longer span is considered as Ly. So if you take the ratio, if it is greater than 2, it should be designed as one-way slab. If it is less than 2, then it will be considered as two-way slab. Okay. If the slabs are supported only on the two edges. So if you look into the diagram of a slab, it contains 4 edges, say AB, BC, and BC, CD, and AD. These are the 4 edges of a slab. So in such a cases, there are 4 edges in a slab. Okay. In case if the slab is resting only on the 2 edges, then irrespective of Ly by Lx ratio, it should be designed as one-way slab. Okay, so this you have to remember. Okay, in case of while designing a slab element, it is usually designed as a planar element. Okay, so the minimum steel reinforcement to be provided in a slab, the minimum amount of steel reinforcement to be provided in a slab depends upon the grade of steel. So for mild steel bars, it is always 0.15% of gross area. That means 0.15 by 100 into B into D. Here, while designing a slab, the breadth of the slab is always considered as 1000 mm. Okay, why we are considering for 1000 mm? So the slab dimension varies from occupancy. So depending upon the room dimension, the slab dimension is also going to vary. So in such a cases, it is difficult to determine the number of bars required. Okay, so in such a cases, we will consider 1 meter strip we will consider the 1 meter strip. Say example, if this is a slab, we will consider only I will consider only 1 meter strip. 1 meter strip. Okay. So 1 meter strip area is considered. 1 meter strip is considered, and the slab will be designed. So that if my slab is having 5 meter, we can easily compute the number of bars required for 1 meter, and you can multiply with the corresponding length. Okay. So in order to make it simpler, in order to make the design simpler, we usually design the slab for a strip of 1 meter width. Okay. In case of deep high strength deformed bars, the minimum steel reinforcement to be provided is 0.12% of gross area. So 0.12% of gross area should be the minimum amount of reinforcement in case of HYSD bars. HYSD bars means either FE 4 on 5, 500, 550 grade bars. In such a cases, we have to consider the minimum area of steel reinforcement as 0.12% of gross area. Here you have to always consider the overall depth. You have to always consider the overall depth. Overall depth should be considered. Okay. So after finding the AST or the steel reinforcement, the spacing of the steel main reinforcement in case of one-way slab shall be lesser of following. The first one is 3 times of effective depth. So here D is effective depth. D is 3 times of effective depth, or 300 mm, or SV is equal to small ast by capital AST, where small ast is area of steel reinforcement. Area of steel reinforcement of 1 bar. Say example, if you are providing 8 mm dia bars, so small AST is pi into 8 square by 4. Okay, so capital AST is the area of steel required for the entire section. So that is the area of steel required to resist the moment. So that is capital AST into 1000. Why we are multiplying 1000? Because in order to, since we are designing for a 1 meter width strip, so we are multiplying with 1000. Okay. So in case of, so along the shorter direction, in case of one-way slab, while designing a structure along the shorter direction, we will provide the main reinforcement. Along the longer direction, that is parallel to the longer direction, we will provide distribution bars. Why we are providing main reinforcement along shorter direction? Because we know that Ly is the longer dimension. So if the length is more, the deflection will be more. Okay. So in order to avoid the deflection, so this is, if it is Ly, if you consider this as Ly, in order to avoid the deflection, what I have to do, if I provide the reinforcement parallel to the Ly, what happens? The slab is going to bend. The slab is again going to bend and show excessive deflection due to the excessive self weight of the reinforcement also. Okay. So in order to avoid that, the main reinforcement is always provided perpendicular to the longer direction. Okay. So the main reinforcement is provided perpendicular to the longer direction. Next, coming to the distribution bars, the spacing of the distribution bars shall be lesser of following. The first one is 5 times of effective depth, 450 mm, or SV is equal to small ast by capital AST into 1000. So this is the minimum amount of reinforcement minimum spacing, maximum spacing to be provided in case of distribution bars. Okay. In case of two-way slab resting on walls on all the four edges, the main reinforcement has to be provided in both the ways, and the spacing of the main reinforcement is similar to the main reinforcement of a one-way slab. Main reinforcement of a one-way slab. Okay. In certain cases, the slabs are not simply supported over the certain portion, okay, over the edges, over all the edges. In such a cases, we have to calculate the bending moment as per the table number 26. In case of two-way slab, which is resting on the walls on all the four edges, then such a type of slabs are, in order to calculate the moment of such a type of slab, we have to make use of table number 27 in order to get table number 27 of IS 456. In case of all the four edges are resting on a wall. In such a cases, we have to use, in order to calculate the moment, we have to refer table number 27. Okay. So in case if the slab is partially restrained, there will be a 9 condition for which the slab has to be designed. Okay. Location of the panel. Here panel is nothing but slab. Depending upon the location of the panel, we have to compute the moment using this moment coefficient. So here the alpha x and alpha y values has been given. Alpha x and alpha y, this is the last column represent the alpha y value, and the remaining column represent the alpha x value, and this alpha x depends upon the Ly by Lx ratio. So for say example, for interior panel means all the edges will be continuous. So in case all the edges are continuous, what happens? There will be a partial restraint on all the four corners. So as a result, what happens? There will be a negative bending moment induced in the slab due to the partial fixity. Okay. So in such a cases, we have to design the slab for both the negative as well as positive moment, and we have to provide the reinforcement according to the negative and positive moment. Here the negative moment coefficient is indicating that it is a hogging bending moment. So near the support there will be a hogging bending moment. So this the table number 26 of IS 456 2000. Okay. So depending upon the type of panel, say example, if one of the short edge is discontinuous, then you have to refer case number 2 in order to calculate the moment. So while calculating the moment, the formula we usually use is mx along the shorter direction. Moment along the shorter direction will be equal to alpha x into w into Lx square, where alpha x is the moment coefficient taken from table number 26. So this formula holds good for two-way slab which is resting on the walls on all the four edges. Okay. So formula is same, but the coefficient alpha x has to be taken as per table number 27 in case of slab which is resting on walls on all the four edges. Okay. So depending upon the end condition, we have to consider the moment here. Okay. So in case of partially restrained or completely restrained slab, we might have to provide an extra torsional reinforcement, because at the support there will be an hogging bending moment. If it is a continuous support, there will be a hogging bending moment. Result lifted in the upward direction. In order to prevent that lifting, if especially in case if the slab edges are discontinuous, we might have to provide the torsional reinforcement in order to avoid the torsion effect on the slab. Okay, so in order to avoid the torsional effect on the slab, what we have to do, we have to provide the torsional reinforcement. So this torsional reinforcement has to be provided only at the discontinuous edges, not on the continuous edges. And the amount of reinforcement, the amount of torsional reinforcement, say AST torsional should be always equal to 3/4 of maximum amount of AST required. Okay, so AST required at the mid span, what we compute, among which we have to take the 75% of the AST as torsional reinforcement, and has to be provided in the form of a mat, in the discontinuous edges only. Okay, in the minimum strip length of Lx/phi in both direction has to be provided at discontinuous edges. Say example, if you consider one slab ABCD, now on the edge J, on the vertical edge J, so here this slab will come and end here, and this slab will on the support at this point. Okay, support at this point. In such a cases, it is not continuous over this portion. This here also it is not continuous over. It is not extending over the point A. That means at this point the support is discontinuous. It is not continuously, the edge is not continuously running on this point. Okay, so this point is called as discontinuous edge. So in such a cases, we have to provide the torsional reinforcement, which is equal to 3/4 of the AST, and it has to be provided for a minimum strip of Lx/phi. Okay, so this length should be minimum Lx/phi. In both the direction, it should be minimum Lx/phi. The torsional mat has to be provided for a minimum length of Lx/phi. Okay, so this mat has to be provided both at the top as well as bottom. Okay, so this amount of reinforcement has to be provided both at the top and bottom. Okay, both at top and bottom, this reinforcement has to be provided. In case of point B, the slab is extended over B on the upper side, and to the right side of point B, the slab is not extended. So this is discontinuous edge and this is continuous edge. Here, both the edges are discontinuous. Okay. In point D also, the longer edge is discontinuous. The longer edge is discontinuous, and shorter edge is continuous. Okay. In case of point C, both the edges are continuous. We should not provide the torsional reinforcement at both the edges are continuous. In case of in the points or in the corners, in which one edge is continuous and the other edge is discontinuous. We have to provide the torsional reinforcement, half of the torsional reinforcement what we have calculated here. Okay, so here you have to provide AST/T/2. Okay, so you have to provide half of the torsional reinforcement. Okay, so here also you have to provide the torsional mat for a length of Lx/phi along shorter direction as well as longer direction, but the spacing of the bar will be doubled. Okay, so the spacing of the bar will be doubled. In case of point C, here both the edges are continuous. Here both the edges are continuous. In such a cases, if both the edges are continuous, you need not to provide the torsional reinforcement here. Okay, you need not to provide torsional reinforcement here. Here also at point D, one edge is discontinuous and the other edge is continuous. So here the half of the torsional mat has to be provided. Is T divided by 2 has to be provided at this edge. So this is about the torsional reinforcement. So in slab, they will the probable question is they may ask you to find out the spacing of the reinforcement, or they may ask you regarding they will give the end condition, they will give mention the end condition, and they may ask you whether we have to provide the torsional reinforcement or not. Okay, so that type of questions can be expected in case of slabs. Okay, so the very important parameter is here you have to remember the spacing of reinforcement. Okay, and also the diameter of the bar. The diameter of the bar should not be greater than 1/8 of thickness. Okay, thickness by 8. If the slab thickness is 150 mm, 150 divided by 8 is 150 divided by 8 is 18.75 mm. So the maximum diameter of the bar should not exceed 18 mm. Okay, this thing you have to remember. And the spacing of the main reinforcement should be lesser of following. First one is 3 times of D, second one is 300 mm, third one is small AST by capital AST into 1000. So these are the things that you have to remember in the slab. So moving on, the next important structural element what we have to discuss is columns. So before going to the design concept of columns, let's see the important definitions what you have to remember for 1 marks as per the IS code recommendation. Okay, so among which the first one is column. So column is a compression member with an effective length the compression member is called as column only if the effective length of the column is greater than 3 times of least lateral dimension. Okay, so if you write the 3-dimensional diagram of a column, okay, so one will be B and the other dimension will be D, and let us call this as L. Okay, so if the effective length is greater than 3 times of least lateral dimension means among the cross section which is less dimension, either B or D. Say example, if B is 200 mm, D is 500 mm, D is 500 mm, then B is the minimum value. Then if the effective length of the column is greater than 3 into 200, that is 600 mm, then such a type of compression members are called as columns. Okay, so columns, we will design the section as a compression member as a column if the effective length of the column exceeds 3 times the least lateral dimension. The second important definition what you have to remember is slenderness ratio. So the slenderness ratio is nothing but it is the ratio of effective length to the least lateral dimension. Okay, so effective length to the least lateral dimension ratio will be called as slenderness. Okay, this is very, very important. In case of column design. You might have already studied in the strength of materials. The strength of materials in the 3rd semester, in the strength of materials, you might have studied the columns and struts, where the columns usually going to fail by two criteria. One is crushing, second one is buckling. Okay, so the buckling plays a very important role in the design of column. Okay, so the buckling of column, whether the column is going to buckle or not, depends upon the slenderness ratio. Okay, so the slenderness ratio is defined as effective length to the least lateral dimension. Least lateral dimension will be considered as slenderness ratio. If the slenderness ratio is less than 12, then it is classified as the short column. Okay, if the slenderness ratio is less than 12, we will classify that type of column as short column, and most of the time it will fails by crushing. It will fails by crushing. So due to the excessive compression force, it is going to the when it exceeds the compression carrying capacity of the section, it is going to the column is going to crush down. As a result, the failure is going to happen. In case of long column, that is, if the slenderness ratio, which is usually represented by letter lambda, okay, is greater than 12, then it always fails by, it most of the times fails by buckling. What is buckling? It is going to create it is going to bend in the lateral direction, so that is called as buckling. So due to buckling effect, the column will fail. Okay, so which doesn't mean, which does not mean that we should not provide the long columns in case of structure. It is always preferred to provide short columns. In case of in case of inevitable conditions, we have to consider the extra moment into the account while designing a long column. Okay. Then the next important thing is effective length. Effective length is the height of the column between two point of counterflexure or point of inflection will be considered as effective length. So in order to determine the effective length depends upon the end condition. You have already studied the various theory in order to find out the effective length of the column. You might have studied the Euler's theory, and in order to measure, in order to find out the theoretical effective value, you might have used the Euler's theory and Rankine's theory. So as per theoretical value, if the columns are effectively held in position and restrained against rotation at both the ends, okay, in such a case, the theoretical value is 0.5, then the effective length will be considered as 0.5 times of L, okay, as per the theory. But in practice, we will always, it is always recommended to use 0.65 times of L while designing a structure. So while designing a column, we have to consider the effective length. So in order to find out the effective length, so we have two methods. One is theoretical method, and the practical recommended value has been given in the IS 456 table number 28. So if both the ends are restrained and effectively held in position against the rotation, then the effective length shall be taken as 0.65 times of L, where L is the unsupported length. Okay, where L is the unsupported length. Effective held, case 2, effectively held in position at both the ends, restrained against rotation at one end. So if the one end is restrained against rotation and the other end is free against rotation, then in such a cases, the effective length shall be considered as 0.8 times of L. So theoretical value is 0.7 times of L, but the recommended value is 0.8 times of L. As per the practical requirement, it will be considered as 0.8 times of L. So if both the ends are effectively held in position and but not restrained against rotation, then the effective length shall be taken as 1 times of L. Okay. Similarly, we have 7 cases which is given in the IS 456 table number 28. Okay, so if both the effectively held in position and restrained against rotation at one end, and the other end is restrained against rotation but not held in position. So here it is not held in position, it is allowed to sway. Okay, in such a cases, the effective length shall be taken as 1.2 times of L. So similarly, we have another 3 cases as per the IS 456 2000 table number 28. Next, if the effective length is greater than 3 times of least lateral dimension, we will call it as column, or we will design it as column. If the effective length is less than 3 times of least lateral dimension, then it will be called as pedestal. Okay, so this pedestal is usually provided in the case of bridges. Okay, so you might have seen the bridges in the abutment portion. Between the abutment and deck slab, there will be a short member. So this member is subjected to axial compression, and these members are usually called as pedestal. These members are usually designed as a pedestal. So the pedestal is the one which is a compression member. A compression member will be called as pedestal when the effective length of the member is less than 3 times of least lateral dimension, then it will be called as pedestal. Okay, so all the columns are usually classified into 3 categories. One is based on the type of force acting. It can be classified into 3 categories. First one is axially loaded column. Second one is axial load with uniaxial moment. Third one is axially loaded column plus biaxial moment. What is loaded plus uniaxial moment, that we will discuss later. Okay, so in the next slide we will discuss. Okay, so for time being, axially loaded column means the column which is in which the reactions or the load coming on the column will be at the center of the column. Okay, so such a type of columns are called, if the load is acting here, if the load coming from the beam or a slab is acting exactly at the center, then it will be called as axially loaded column. So here there is no moment due to the applied load. Okay, so if you write the elevation, so your load, if the load is acting at the junction of 2 axes, so here the one axis is called as minor principal axis, and this one is called as major principal axis. So the one which is parallel to longer direction will be called as major principal axis, and the one which is parallel to shorter dimension will be called as minor principal axis. So if the column, if the load is acting exactly at the junction of the minor principal and major principal axis, then such a type of columns are called as axially loaded column. So here there is no eccentricity. So in such a cases, we will design the column only for the axial load. Okay. So in certain cases, it is not feasible to place the beam or a slab exactly at the center. So in such a cases, there will be certain amount of, we will place somewhere on the column. So as a result, there will be an eccentricity. So this is called as eccentricity along x direction. Similarly, this is the deviation from the axis. So this is eccentricity along y direction. So this eccentricity, there will be an eccentricity in the column. So as a result, there will be an extra moment induced on the column. So as per IS 456 specification, we have to design a column, even though it is an axially loaded column, we have to design the column for a minimum eccentricity. Okay, so what is this minimum eccentricity? The minimum eccentricity is equal to the unsupported length divided by 500 plus least lateral dimension, or 20 mm, whichever is greater, that should be considered as minimum eccentricity. So we have to design, if the load is acting here, instead of load acting here, eccentricity. So as a result, there will be an extra moment induced along with the load. So this is called as moment along x direction. Okay, so there will be a moment induced in the due to the eccentricity. So that moment may be in the one direction or it may be in the both the direction. If the eccentricity is about both the axes, then there will be a two moments. That type of columns are called as axially loaded plus axially loaded biaxial moment column. If the eccentricity is only in the one direction, say example, this is the column. Instead of placing the section here, if I place the section somewhere here, okay, if I place the beam somewhere here, so here there is a eccentricity only in the x direction, then there will be a moment in the y direction which is equal to pu into ex. Okay, so this type of columns are called as axially loaded uniaxial column. Okay, however, even though it is axially loaded column, we should design the column for a minimum eccentricity of unsupported length divided by 500 plus least lateral dimension divided by 30 or 20 mm, whichever is greater, so that it will be, the column section will be always safe even though there is a small amount of eccentricity. So if there is a small amount of eccentricity, there will be a moment induced. So as a moment induced, it tries to bend the column. It tries to bend the column. So as a result, the buckling is going to happen. Okay, so the column may fail due to buckling. So in order to avoid that, we should always design for a minimum eccentricity. Okay. Next, coming to the types of column, as I told you, there will be three types of column: axially loaded, axial load with uniaxial moment column, axial load with biaxial moment. How to identify this axially loaded, uniaxial moment, and axial load with biaxial moment? If you consider a layout of a column, okay, if you consider a column layout, okay, if you consider a column layout here, if you consider the interior column, if there is certain eccentricity, these beams will be provided in a straight line. Okay, even though if there is a certain eccentricity, okay, the moment induced by eccentricity from this beam will transfer the load to the column at this point. Okay, so as a result, if there is while transferring, if there is certain amount of eccentricity, it will try to create a moment in one direction. Okay. Similarly, here on the other side, this beam is also going to create a moment in the opposite direction. So here, the moment created by this beam and the moment created by this beam get nullified. So along the x direction also, here also, the moment created by this beam and the moment created by the eccentricity due to this beam will get nullified. So as a result, there will be only an axial force which is transferred into the column. So this type of column, the number one will be the interior columns will be always designed as the axially loaded column. Okay. So if you consider the corner columns, okay, if you consider the peripheral columns, let us consider. There, in case of peripheral column, the moment created due to the eccentricity of this beam will be there. Okay, so due to this eccentricity, there will be a moment in one direction. So that type of columns are called as axial load uniaxial moment. That means it is creating the moment in only one direction. So such a type of columns will be called as peripheral columns, or called peripheral columns, except corner columns will be designed as axial load with uniaxial moment. If you consider the column number 6, 7, 8 and 9, okay, 6, 7, 8 and 9. So in this case, on the both the edges are discontinuous. Okay, both the beams are discontinuous at this point. So it will create the moment in both the direction. So such a type of columns will be designed as axially loaded biaxial column. Okay, axially loaded biaxial column. So the things to be remembered in case of design of axial column is, the first one is the load carrying capacity of the column. The load carrying capacity of the column is given by Pu is equal to sigma Cc into AC plus sigma Sc into AC. So where sigma C is the Cc is the amount of, or the stress, maximum stress resisted by the concrete section, maximum stress resisted by the concrete section. Okay, so the sigma Cc will be always equal to design strength. We know that the design strength from the stress block parameter as 0.446 FCK. Okay, so 0.4, so this equation will become 0.446 FCK into AC plus, if you consider the stress, corresponding to 0.02 percentage of strain. Okay, 0.02 percentage of strain. 0.02 percentage of strain, the corresponding stress will be 0.75 times of Fy. So if you under the compression, if you consider the stress corresponding to 0.02 percentage of strain, then it will be 0.75 times of Fy. Okay, so stress will be 0.75 times of Fy. So this will become 0.75 Fy into AC. So in general, the load carrying capacity of the section will be taken as Puz will be equal to 0.45 times of, they have rounded off to 0.45. Okay, 0.45 times of FCK into area of concrete. So area of, if you want area of concrete, you have to deduct the area of steel from the gross area. Okay, so area of concrete is equal to Ag minus ESC. Okay, for a minimum eccentricity, so this formula is applicable. This formula is applicable only for axial columns. Only for axial columns. Okay. However, for uniaxial column and biaxial column, or the axial column with minimum eccentricity, what we discussed in the previous slide. Okay, so the minimum eccentricity, as we discussed in the previous slide. In such a cases, the total load carrying capacity of the concrete shall be taken as 90%. So if you multiply the 90.9 to the equation number 1, you will get the equation 2. So this should be used while designing a column which is subjected to a minimum eccentricity. So in the problems they will mention subjected to minimum eccentricity, or in sometimes in the problems they will mention it as neglecting the eccentricity. Okay, so if they mention neglecting the eccentricity, you have to use the equation number 1. Okay, or in general, when the E minimum is less than or equal to 0.05 times of B, use equation number 2. Okay, if when the E minimum is less than or equal to 0.05 times of B, use equation number 2. When E minimum is greater than 0.05 times of B, then use equation number 1. Okay, so the important point to be remembered here is, if they mention as axial column neglecting the eccentricity, you have to use equation number 1. If they mention a column with minimum eccentricity, then you have to use equation number 2 in order to calculate the load carrying capacity of the column. Okay, load carrying capacity of the column. So moving on to the further IS code recommendations. So as per IS code, IS 456/2000, the minimum least lateral dimension for a column should not be less than 200 mm. Okay, that means the breadth or the depth what you design, should be of 200 mm wide. So minimum B or D should be equal to 200 mm. Okay, and the minimum nominal cover for the column should be 40 mm. You have to minimum provide a clear cover of 40 mm for a column, and the diameter of the main bars shall not be less than 12 mm. So in order to use the reinforcement in a column, the minimum diameter to be used is 12 mm. Okay, so in certain cases we may not be able to provide the width of with a least lateral dimension of 200 mm. In such a case, say example, if you are providing a canopy, if you want to make it as a proput cantilever, in such a cases, the size of the column is usually the size of the column required is very much lesser, because the load coming on the column will be very small. Okay, in such a cases, if non-avoidable condition, if the least lateral dimension is less than 200 mm, then the minimum nominal cover should be 25 mm. Okay, so but in general it should be greater than 40 mm. The minimum nominal cover should be greater than 40 mm, and the minimum diameter of the bar in such a cases can be less than 12 mm. Okay, and the minimum amount of steel reinforcement in a column should be 0.8%, whereas for maximum amount of reinforcement is 6%. So but from the practical point of view, the maximum amount of compression reinforcement is usually restricted to 4% of the gross area. Okay, so whenever we use the reinforcement without overlapping, that means, say example, if you want to provide a column for 2 floors, okay, if you provide the reinforcement without any overlap, say example, if the height of the floor is 6 meter, if the height of the floor is 3 meter and 3 meter each, okay, 3 meter each, if you provide the reinforcement for a column in a single stretch, okay, without any overlapping, then in such a cases you can provide up to 6% of the gross area. Okay, if you can provide up to 6% of the gross area. If there is a overlapping of bars, in certain cases, in certain cases, we may not be able to provide the single bar on a entire stretch. We might have to make a overlap. Okay, we might have to make a overlap. In such a cases, the maximum amount of compression reinforcement is restricted to 4%. Okay, and the minimum number of bars to be provided in case of circular section is 6, and that of rectangular section or a square section is usually around 4 bars. So if it is a rectangular or a square column, you have to provide minimum amount of 4 bars, minimum of 4 bars. Minimum 4 bars has to be provided. In case of circular columns, you have to provide minimum 6 bars. Minimum 6 bars has to be provided in case of circular bars. So, and coming to the pitch, coming to the lateral reinforcement. Okay, so the IS code specifies that the maximum spacing between the two longitudinal reinforcement. Okay, so if you consider the cross section, if you provide the 4 bars as a reinforcement, the spacing between the two bars, in any direction should not be greater than 300 mm. Okay, so the maximum spacing is equal to 300 mm. Okay, if it exceeds 300 mm, you have to provide another reinforcement, and the reinforcement should be always distributed equally. That means it has to be provided in the even numbers. It should not be provided in the odd numbers in case of columns. And coming to the lateral or transverse reinforcement, the main role of the longitudinal reinforcement is to transfer the load, compression load, from the higher in case of longitudinal reinforcement, the main role is to transfer the compression load into the footing effectively. Okay, so the main purpose of providing lateral ties are in order to hold the longitudinal bars effectively in position without causing the buckling. Okay, so in order to avoid the buckling, we usually provide the lateral ties. Okay, so while using the transverse reinforcement, the minimum diameter of the transverse reinforcement to be used is should not be less than 1/4 of the longitudinal steel diameter, or 6 mm, whichever is greater. Sorry. Okay, say example, if you are using 32 mm dia bars for main reinforcement, so 1/4 of 32 mm is 8 mm. Okay, 8 mm or 6 mm as per this one. Okay, so you have to select the lateral ties as 8 mm. Okay, in this case you have to select the lateral ties as 8 mm. So minimum diameter should be greater than 1/4 of the longitudinal steel diameter, and 6 mm or 6 mm, whichever is greater. So that should be considered as diameter of the lateral ties. And the spacing between the lateral ties, shall be considered as lesser of the following. The spacing shall be lesser of the spacing in the lateral ties will be generally called as pitch. Okay, so the pitch should be always considered as lesser of following. First one is 16 times of diameter of a longitudinal bar, least lateral dimension, or 300 mm. So whichever is lesser, that should be considered as maximum pitch. Okay, so the maximum pitch should be least of those things. So let's move on to the few previously asked questions, which is usually repeated in the gate examination. So the first question is, the lateral ties in a reinforced concrete rectangular column under axial compression are used to. First option is avoid the buckling of longitudinal steel under compression, provide adequate shear strength, provide adequate confinement to concrete, reduce axial deformation on column. So the correct answer is uh, the correct answer is the option A, avoid the buckling of longitudinal steel under compression. In order to provide adequate confinement to concrete, we will provide formwork. Okay, not the lateral ties. Okay, so the correct answer is option A, avoid the buckling of longitudinal steel under compression. So that's why I told you here the lateral ties are provided in order to avoid the buckling of longitudinal steel reinforcement, so that there will be an effective transfer of load from floor to floor. Okay. In the next question, in reinforced concrete, pedestal is defined as compression member whose effective length does not exceed its least lateral dimension by option A 12 times, option B 3 times, option C 16 times, option D 8 times. As we discussed in the previous slides, the compression member will be called as pedestal if the least lateral dimension is less than, if the effective length of the compression member is less than 3 times of least lateral dimension. So the correct answer is option B. It is 3 times the least lateral dimension. So if the effective length is less than 3 times of least lateral dimension, it will be pedestal. If effective length is greater than 3 times of least lateral dimension, then we will call it as column. Okay, please remember this. In one of the gate examination, they have asked us to find the minimum eccentricity of for a column. Okay, they have given a column of size 450 mm by 600 mm, has unsupported length of 3 meter and is braced against sideways in both direction. According to IS 456 2000, the minimum eccentricities with respect to major and minor principal axis are dash. They have given the option as 20 20, 26 21, 26 20, 21 and 15. In order to solve this type of problem, you have to, so the cross section dimension is given, 450 mm is the breadth and 600 mm is the depth. The minor principal axis is the axis which is parallel to smaller dimension, minor axis. Okay, the axis which is parallel to major dimension is called as major axis. Okay, so we know that we know that in a column we have to design it for a minimum eccentricity. So the minimum eccentricity is given by E minimum is equal to unsupported length. We have the formula unsupported length divided by 500 plus least lateral dimension by 30. So first we have to calculate the I will calculate along shorter about minor axis, so parallel to minor axis. So the effective length is, or unsupported length is 3000 mm. So the column is, since the column length is given as 3 meter, I am considering as 3000 divided by 500 plus least lateral dimension. So for we are considering the minor axis. We are considering the minor axis. For the minor axis, the least lateral dimension is D. Okay. So what is this? D is 600 mm divided by 30. It will be 3000 by 500 is 6. 600 divided by 30 is 20. It will be 26. Okay. So on another direction, or 20 mm, whichever is maximum. In this case, the maximum is 26. So I will consider E minimum along y direction. E minimum along y direction. Sorry, E minimum along x direction. E minimum along y direction is unsupported length is again 3000 divided by 600 plus, sorry, 6 divided by 500 plus 600. What is in the major principal axis, the least lateral dimension is B. B is 450 mm. 450 divided by 30. It will be 21 mm. Okay, or 20 mm, whichever is greater. So in this case, 21 mm is higher, so I will consider 21 mm. So the correct answer is 26 and 21. So the option B is the right answer. This is how you have to solve this problem. Next, a RC short column with 300 mm by 300 mm square cross section is made up of M20 grade concrete and has 4 bars of 20 mm dia of Fe415 steel. It is under the action of axial compression with minimum eccentricity. So in case of axial compression with minimum eccentricity, what is the formula to be used? Okay, axial column with minimum eccentricity, we have to use the equation number 2. Okay, we have to use the equation number 2. If they mention it as only axial column with neglecting the eccentricity, then you have to use the equation number 1 in order to find out the load carrying capacity of the column. Okay, so in this case, they have mentioned that axial compression member with minimum eccentricity. So since they have mentioned it as minimum eccentricity, we have to use the equation number 2. That is Pu is equal to 0.4 times of FCK into AC plus Fy, sorry, 0.67 times of Fy AC. Okay, this formula has to be used. Further, they have mentioned that ignoring the reduction in the area of concrete due to the steel bars. They have mentioned that while calculating the area of concrete, what is the formula in order to find out the area of concrete? Area of concrete is always equal to Ag minus AC. Ag minus AC. Okay, so they are mentioning that you neglect the amount of reduction of area of the cross section due to the area of steel. So here area of steel should be considered as 0. Okay, in order to calculate the area of concrete, you should mention the ASC equal to Ag. Okay, so that is the meaning of ignoring the reduction in the cross section area due to the steel bars. The ultimate load carrying capacity of the column is, so substitute in this, FCK is given, area of concrete is 300 by 300 and Fy is given Fe415. Fy is given as Fe415 and area of steel reinforcement, compression reinforcement is given as 4 bars of 20 mm dia. So 4 bars of 20 mm dia is AC is, it will be 314 mm square. Okay, so if you substitute that in the below formula, you will get the Pu value as 1069. Okay, so the correct answer is 1069 kilonewton. Okay, so coming to the last problem, a RCC column, with a RCC column with lateral ties of rectangular cross section in is 250 mm by 300 mm, reinforced with 4 numbers of 16 mm dia bars. The grades of steel and concrete are Fe415 and M20 grade respectively. Neglecting the eccentricity effect, the axial load carrying capacity of the column is dash. So here they are mentioning it as neglecting the minimum eccentricity condition. That means for purely axially loaded column. Okay, for purely axially loaded column, the equation is PUZ is equal to 0.45 FCK into AC plus 0.75 FY into AC. If you substitute into this formula, it is 0.45 into FCK is 20, area of the concrete. Here they are not mentioning, neglecting the steel reinforcement area. Reduction in steel reinforcement area has not been mentioned. So area of concrete should be equal to AG minus ASC. What is AG? AG is 250 by 300 minus area of steel is 4 into pi into 16 square by 4. Okay, so 250 into 300 minus area of steel is around 74195 mm square. Okay, so 0.74195 mm square plus 0.75 into Fy is 415. Area of compression reinforcement is 4 bars of 16 mm. So if you substitute that, you will get the answer. You will get the answer as something around 0.45 FCK into okay, you will get the answer as 918.07 kilonewton. Okay, so this is the answer that you have to consider. Thank you, all the best. And one of the friend has asked us to explain the discontinuous edge in slide number 40 again. Okay, moving on to slide number 40. Okay, let me clear this and write once again. Okay, in case of discontinuous edges, we have to provide the torsional reinforcement in order to avoid the lift, in order to avoid the torsional effect. So usually the corners will be held down against the lifting up. Okay, in such a cases there will be a moment induced due to the partial fixity. So as a result, there will be a torsional effect induced on the slab. So in order to avoid that, in order to resist that torsional forces, we have to provide the torsional reinforcement or a torsional mat. So the area of torsional reinforcement, ASTT, will be always equal to 3/4 of the area of main reinforcement, 3/4 of the area of main reinforcement. So where we have to provide this torsional mat, we need not to provide the torsional mat at all the edges. Okay, all the corners. We have to provide this torsional reinforcement only at the discontinuous edges. Say example, if you consider the point A, if you consider the corner A, if you consider the corner A, here both the edges are discontinuous. This edge is not extending over the point A, so this corner is point A. Okay, so this is point A. It is not extending over point A, so this is discontinuous. Again, this edge is also not extending over point A, so this is discontinuous. In this case, it is not extending the point B. At the point B, it is not extending over the point B along the horizontal direction. So one edge is discontinuous and the other edge is continuous. Okay, here in this direction, it is continuous. There is another slab. Okay, so this is continuous, this is discontinuous. Again, in this case, here both are continuous. Here both are continuous. In this case, this is continuous and this is discontinuous. Okay, these are the discontinuous and continuous edges. So we have to provide the torsional reinforcement only at the discontinuous edges. If both the edges are discontinuous, we will provide the torsional reinforcement equal to 3/4 of the main reinforcement, main AST. Okay, and the length of this mat and the length of this mat should be equal to Lx by phi in either direction, where Lx is the span along shorter direction. Span along shorter direction. This has to be provided. This has to be provided in the. This has to be provided, which is equal to 3/4 of AST. Whereas in point B, in case of point B, here the one edge is continuous and the other edge is discontinuous. In such a cases, we need not to provide the torsional reinforcement equal to the 3/4 of AST. Okay, so we have to provide the torsional reinforcement half of this. Okay, half of this. So half of this means it will be, the spacing will be doubled. Okay, so the length is same Lx by phi in both the direction. Whereas in point C, at the corner C, both the edges are continuous. Here we need not to provide the torsional reinforcement. Whereas D is similar to corner C. Here we have to provide the torsional reinforcement equal to half of the torsional reinforcement what we have calculated as 75% of the total reinforcement. This amount of reinforcement has to be provided, and this torsional reinforcement has to be provided both at the top and bottom. And someone in the slide, okay, one of the friend has asked in the slide 44, should we have to calculate the minimum eccentricity even if the force is acting exactly at the center of the column? As per IS 456 specification, even though in a column, if the load is acting exactly at the center, we have to design it for a minimum eccentricity of E minimum, which is equal to unsupported length by 500 plus least lateral dimension by 30 or 20 mm, whichever is greater, that has to be designed. Okay. So that's all from my side. Thank you and all the best for the GATE examination. Over to you, Rajit sir.
Thank you, Professor Arjun. It was a very informative session. So instruction to participants. So please find the link for the session feedback and provide your valuable feedback by today 5 p.m. And I request all the participants to join today's second session at 3:45 p.m. using the same YouTube channel link. Thank you.